So remember last time we were getting introduced to these things called the exponential functions, right? And one that we're looking at was 2 to the x, right? So exponential functions. And we're looking at 2 to the x, and we saw it looked something like this. Something like this, and we sort of taken a digression at this point and said, "Oh, isn't it interesting? This function is defined for all numbers, right? It's defined for this function. It looks like it makes, at least the way we've drawn it, looks like it ought to make sense even for irrational numbers." Right? That is, for example, 2 to the pi makes sense, even though when you were in high school or before, whenever you were introduced to the exponential function, probably they didn't explain what 2 to the pi meant, right? I don't think any high school tells you to think of things like 2 to the pi. But you take 2 to a fraction, you take 2 to a whole number, 2 to a negative number, maybe 2 to a fraction, this sort of thing, but not 2 to an irrational number. Now maybe you're starting to get some sense of what that ought to mean. Okay, so that was sort of a digression, and we pointed out that just a fact, which we can't explain at this point. And so whenever I say fact, it's something that I'm just going to hand to you, and it's true, but we can't explain it. Fact that irrational powers behave like rational powers, in the sense that a to the r, a to the s is a to the r plus s, a to the r to the s is a to the rs. Right? The two properties of exponents that you have in the old sense still hold when you extend it to all real numbers, irrational and irrational. Right, so for R and S, any numbers in R, not just rational numbers or whole numbers. Okay, so that's where we stopped last time. Okay, let's think about this graph a little bit. We just said that the domain of this graph is the whole real line, right? It's the whole real line. What's the range? What's the image maybe? Right. What's the image? What kind of outputs? What's the collection of all outputs you get by looking at the graph? Maybe I'll choose Alexa.
Positive numbers?
All positive numbers, right? So you can't get 0, right, by taking 2 to a power. Right? But you can get something pretty small by taking it to a large negative number. Like 2 to the negative 10 is 1 over 1,000, approximately 1 over 1,000. Right? So you can get any positive number you can get. Right? So just positive numbers. Okay. Okay. What's the what's the y-intercept? What's the y? Where does it cross the y-axis? Well, okay, at this point, right, at the value 1, right, it crosses at 0, 0, 1 here, right? Does it have an x-intercept? No, it doesn't, right? So it doesn't cross the x-intercept. Does it have any asymptotes? Sure, right? It's got an asymptote of x equals 0, y equals 0 as right? So as x goes to negative infinity, 2 to the x goes to 0, right? So it says that has a horizontal asymptote of y, the line y equals 0 is an asymptote asymptote as you go towards negative infinity, right? But nothing as you go to positive infinity. Okay. Is this a function, is this a one-to-one function? Is this a function that, does this function ever take two values and return the same value, two different values and return the same value? Right? Are there 2 points that have the same height? No. Right? You see that this function is increasing. Right? 2 to the x is strictly increasing. Right? So you never have two different inputs with for which 2 to the x1 equals 2 to the x2. Right? It's to say it more plainly, using the term that we defined before, it is a one-to-one function. It's a one-to-one function. Another way to say it is that it passes the horizontal line test. Right? If you draw any horizontal line, it only intersects the thing at one point, the graph at one point. Right? And it passes the horizontal line test. Right? Another way of saying it. Okay. Any strictly increasing function or strictly decreasing function will pass the horizontal line test. Will be one-to-one. Okay. Okay. So what? It passes the horizontal line test. So what? So what do we know about this function? A function that passes the horizontal line test. Has an inverse, exactly. Right. So because of that, because it's a one-to-one function, it has right. It has an inverse. The inverse, you see, is going to pass through the point 1, 0, right? It's going to pass through here, 1, 0. And what's going to happen to it? Well, it's going to go like this, right? And we see that the inverse function, of course, has a vertical asymptote, right? Namely the line x equals 0, right? So this guy has a vertical, right? For the inverse function, inverse of x as x goes to 0 from the right-hand side approaches negative infinity, right? Because f as x went to negative infinity approached 0, so the inverse function as x approaches 0 will go to negative infinity, right? That's just the symmetry of inverses. Okay. Okay. Some of you probably know what this inverse is called. Do you know the name of the inverse? Okay, I'll leave it as a mystery.
Is it the log? Is it the log?
It is the log. So this is the so-called log base 2 function. That's how we define the log. The log is the inverse of the x of this. Log base log is the inverse of the log of the x function. Okay. But just pretend you forgot that. Okay. We'll introduce them properly next time. Okay. Any questions on how the exponential function
What
looks?
does it say after it passes?
I think that's a central. the horizontal line test.
Line test, okay.
Yeah. It's not clear to me what it says there. Yeah. Okay. Horizontal line test. Okay. Okay. So a couple of, let me go back here. Okay. Let me ask you this. Okay. What if I look at the function g of x equals 1/2 to the x? What does that function look like? Can anyone tell me right now? What does this function look like? What does this function look like? Carol?
Well, isn't it going to be decreasing?
Okay.
So it's going, the y-intercept is 1, and then it's going to go down, and it's never going to reach 0 because that's the asymptote, but
Right,
it's going to
so-
look like it's about to reach 0.
So like at 1 it'll be a half, at 2 it'll be a fourth, 3 will be an eighth, and 4 will be 16. What about at negative 1?
Then it's going to be
What will be the value?
2.
2, right? Negative 2,
4.
4, right? Negative 3. Okay. So what words am I looking for you guys to say? It's the flip, right? This guy is the flip of that guy, right? This guy is the flip of that guy, and that's actually obvious, right? Because this is 2 to the minus 1 to the x, right? In other words, it's 2 to the minus x, right? In other words, f of negative x, right? If this f of x is 2 to the x, then g of x is f of negative x, right? So it's the flip in time of that guy. So observe this. Okay. Okay. If we maybe just throw in some variations. That's a very important variation. But if I write something like, okay, so let's just 2, 2. So here's f 2 to the x here. Sort of dumb ones. What does negative 2 to the x look like? We're going to put down, of course, right? We multiply by negative 1. This guy's negative 2 to the x. What about well, 2 to the negative x? 2 to the negative x we just said, right? That one is the flip across. This guy's 2 to the minus x, right? Also known as 1/2 to the x, right? Or 2 to the minus 1 to the x. Those are all the same thing. Okay. How about this one? 2 to the x times 2. So,
I would just take a weird random
Yes.
guess, but do you use the rule of a to the power n times a to the power 0 to the power x plus 1?
exactly.
And then you will shift it by 1 to the...
Perfect. Exactly. Okay. So it's the shift of this guy 1 to the left. Right? This guy is the shift of guy 1 to the left. Right? So it's shift 1 to the left to the x. But you also notice it's 2 to the x stretched by 2. Right? If you stretch it by 2, that's the same thing as moving it 1 to the left. Or maybe it's cooler to say moving it 1 to the left doubles it. Moving it 1 to the left doubles it. Moving it 2 to the left multiplies it by 4. Moving 3 to the left multiplies it by 8. Moving it 1 to the right, of course, what does what to it? If I ask you what is 2 to the x minus 1, what does that look like? Well, you could say you take the guy and you move it 1 to the right. But you could also say you take the guy and you multiply it by a half. Right? So if you take every value and halve it, right? every value and take half of it, right? That's the same thing as moving the thing 1 to the right. Lowering.
So you can't say that 2 to the x times 2. Can you say that that's 4 to the x?
No, that's
Okay.
not, that's just equal.
Okay.
Yeah. So the only things that you can do are these: a to the n, a to the n, a to the n plus n, a to the n to the n equals a to the n. That's it.
Okay.
Yeah. That's it. Don't try to be creative and invent new properties. Yeah, I think this happens for a lot of people. They're like, oh, isn't it true that such and such a thing happens? And maybe for some functions it does. But in general, these guys, the functions have certain properties, and that's it. Just like a limited. This function has 2 properties, and that's basically it for this function. Two nice properties. Okay. So that is 2 to the x. So in general, you have these exponential functions. You have some function f of x equals d to the x, and usually you take b to be, and you always take b to be a positive number. Okay, and not equal to 1, because if you took b to be 1, well, your function would be just a constant, right? Because you have powers of 1. Okay. So in general, you have some function that looks like this. B is called the base. The base. I didn't lie, but when my daughter was 2, that was her name for me, the base.
Why?
It's not clear. And she said, okay, your name is the base. You are the base. And I am base helmet. That's her name. Right? Her name was base helmet. And then mom was connectress.
Did she see something like a
It's not really clear watching it. But she'd say, connectress, connectors, go to the base or something. and my wife would be like, what?
How old's your son?
He's 2, so he wasn't with us at that time. Later, after he was born, so his name was Taka, right? So his name was Takanaka.
Do they go together?
Yeah. They don't play very well together. Okay, so, sorry, I just reminded us about the base.
That's not something.
It's not relevant. Obviously not. Okay, so then I might ask you, what does a graph look like? What does a graph look like? Okay. And the answer is, well, what do you think of a graph? The answer is you don't know. I mean, the answer is it depends. And it depends on something. What does it depend on? Well, the base, it depends on the base being either
Positive or negative?
positive. No, the base is always positive.
Oh, I don't know, the exponent is positive or negative?
Well, I mean, we're looking at the graph for all x, right? So, Rebecca?
And then it depends on whether b is either greater than 1 or between 0 and 1.
That's right. Depends on how big b is, right? If b is bigger than 1, well, it's basically going to look like the 2 to the x function, right? It'll be an increasing function, right? So what does it look like? What does the graph look like? It depends. Right? If b is bigger than 1, then it's an increasing graph. find 1, it's going to be b. Well, b, if b is bigger than 1, then it's going to be here, but it will have b squared, b cubed, etc. And b is 1 half of 1. It looks basically like the 2 to the x function. If b is less than 1, right? If b is less than 1 and greater than 0, because we require that they're all greater than 0, then it's going to be a decreasing function. Right? It will look like the flip of the 1 over b function, right? Where 1 over b is bigger than 1.
So that would be like 2 to the negative.
Yeah, right, because 2 to the negative, so looks like 2 to the x, here looks like 1 half to the x, right? In other words, that is 2 to the negative x. It will look like the flip of one of the guys where the base is bigger than 1. Okay. And there's one base. Which occurs naturally. Okay, it's sort of like more important than the other ones. And maybe you know what it is. What is it? There's one base that people consider to be the natural base. Okay, Alex.
Natural?
What's the base of the natural law?
Or is it 2?
Somebody shout it up. What is it?
E.
E.
Oh.
This thing called E.
Oh yeah, then you just like flip it. Oh,
This thing
it's all
called
come back to me.
So E, if you, it's a number, it's sort of a peculiar number. One way you can get it is by taking an infinite sum. You could take the sum of things like 1 over n factorial as n goes from 0 to infinity. That is 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, etc. If you keep on going, this sequence of numbers, 1 plus 1 plus a half plus a sixth plus a 24th plus 1 over 120 plus etc. These things tend towards a particular number that occurs over and over in mathematics. And that number is given a name called E. Okay. E for Euler. E for Euler, a mathematician. Okay. And so people usually call e to the x the exponential function. The exponential function, because people are talking about some exponential function that terminates this one. And I know one book, one very famous book that begins with the line, e to the x is the most important function in mathematics. I think that's true.
Does this mean we're going to get to 13s or
No?
Yeah. How do you do it without?
This is a course about, so we'll learn a lot about it, right? But as for using a calculator, that's not. I'm afraid that's not. What I'm trying to get to you guys is the ideas, right? The ideas, more so than. You do calculations, but nothing that requires you to, nothing that needs a calculator. Yeah, sorry.
That's all right.
Yeah, this must be a disappointment.
No.
Okay. Okay. So E, it's not. We think of this as sort of a naturally occurring number like pi, for example, and not like the number 10. Right? So maybe for us we might think 10 is a natural number, right? We've got 10, but why? What's natural about 10? Why do we use 10? What's natural about 10?
Well, you use it in logs because it's the easiest way to take a log of a number. Because you can take the 10 log of any number.
Well, you can, there's actually more, so you can actually take the log of any, you can use any base. Any base is okay, right? Why do we use 10? Okay,
I heard we use 10 because we have 10 fingers.
because we have 10 fingers. This is actually the real reason, right? What's the reason, so 10 is natural in the sense that it occurs in nature, right? That in the sense that we have 10 fingers. But if you went to another planet and said, oh yeah, we write all our numbers, in 10, right? When I write something like this, I mean, what I mean is 2 times 10 squared plus 1 times 10 plus 1 times 10 to the 0. Right? They would say, well, why do you use 10? We have 11 fingers here. We write our numbers in base 11. Right? There's actually nothing. It's sort of natural to our planet. Natural to humans. Natural to humans.
I heard this my teacher was telling me something really interesting, and he was like, well, if we didn't use 10 as like the way such an important number, like pretty much like all civilizations wouldn't have really worked, because without using 10, like you can't really do a lot of like math. And you can't build things and like do architecture, and it was an interesting theory, I thought.
It's not true, actually. It's not true. Yeah, I wouldn't say that, because you can, if you use 2 as a number, 2 as your base. Well, you can make your entire number system based on 2. There's nothing special. There's nothing special about 10. Right? You could use 2 just as we do in computers use 2. Right? So you write, if somebody writes like 110, and the computer writes you this message 110. Right. What the computer says really means is 1, 2 squared, plus 1, 2 to the first, plus 0, 2 to the 0. Right. This is so-called binary thing. So this would be for a human being, this is going to be like 4. This is 6. Right? This is 6 for the humans. There's actually nothing particularly special about this number, except that humans have 10 fingers. However, if you went to another planet, the aliens would say, we have 2 fingers. I don't know what you're talking about. But if you show them E, they would say, oh yeah, we know about E. Right? E is something that actually occurs mathematically, naturally mathematically. Yeah. So I'm not sure what your teacher meant, Alex. But at least
I'll not explain it as well as he did.
okay. Yeah, but from a mathematical point of view, there's nothing particularly special about 10, right? Okay, so there's this base, right? There's the natural, the exponential function. Okay, f of x equals e to the x, right? Where e is this number, is this number, and you might be wondering, what's so good about it? What's so good about it? Okay, what's so good about this number? When we take this thing as a base, is there anything special? Is there any sort of special phenomenon that occurs? So here's one thing that happens. Let's recall the average rate of change of some function over a b. Okay, so we have some function, right? We have some function a, b, f, Okay,
The first function minus the second function.
there's only one function.
Oh, yeah, direction.
There are 2 points now.
But basically like the y's minus each other over the x's.
The change in the function over the change in the input, right? And so f of b minus f of a over b minus a, and this thing is the average rate of change. Right? Everyone remember that? Okay, right, and graphically, it looks like this, right? The change in y over the change in x, right? And geometrically, it is the slope of the so-called secant line. The slope of the secant line, right, through those 2 points. Okay, just to sort of quickly remind us, if we look at the function x squared, okay, so here's the x squared function, right? Here's 1, and let's go to 1 plus h. F of x is x squared, right? Can somebody tell me the rate of change over this interval? Lauren?
So it would be 1 plus h squared minus 1 squared over h.
So you get 1 plus h squared minus 1 squared over h, right? Right, you get f of 1 plus h minus f of h, f of 1 over b minus a. Right, so you get 1 plus h squared minus 1 squared over h. Right, let's work it out. That's, of course, 1 plus 2h plus h squared minus 1 over h. Right, that is to say 2h plus h squared over h. The ones cancel each other off. Right, and so we get 2 plus h, right? Canceling h out of the top and bottom. Right? Okay, so we have 2 plus h.
As what is that?
That is the slope. That is the rate. That is the average rate of change over this interval. Or another way of saying it, it's the slope of the line through these 2 points. Everyone remember that? Sorry, you look a little.
No, I
Right? So we just have this interval. We have the function. Right? Here we have this function, the x squared function, and we're just calculating the rate of change over this interval. Okay. So for example, over the interval 1, 3, what's the average rate of change? Well, in that case, right, if this point is 3, then what's the average? What's the rate of change? Well, h is going to be what? 2, right? Over 1, 3, the average rate of change is, h is 2, so we get 2 plus 2, that's 4. Right? Over 1, 1.1, what's the average rate of change? Well, what's h in this case? H is 0.1, right? So we get 2.1.
Sorry, where are we getting the 1.1?
I just made it up.
Oh.
Okay, so I'm,
You're just doing the vector.
yeah, I'm saying let's take some. What about over this interval? What's the rate of change?
Okay.
What about over this interval? What's the rate of change? What about over 1 comma 1.01, what's the rate of change?
2.01.
2.01. What about 1 comma 1.00000001?
2.00.
Yeah, the rate of change is 2.000. And so what you see is that the slopes of these lines, as you take the second point closer and closer, what do you see about the slopes? The slopes get closer to what? 2, right? Slopes get closer to 2. Okay. So let me draw a picture that's better here. Right, here we have this thing, and what we see is that, basically if we take these slopes, the slopes of different secant lines, right? The slopes get closer and closer to, a slope closer to a slope of 2. Right? This is what's called, this line that just touches it is called the tangent line. This line that just touches it is called the tangent line. And what people usually say is that the slope of the tangent line is 2. So, slope of tangent line is 2. Yeah, Caroline.
Is that applicable to e to the x?
So e to the x is something funny. So right now we're thinking about this function f of x equals x squared. Okay. And here it is. What's the slope of the tangent line here at x equals 0? Well, you have this sort of line, right? The tangent line is flat line, right? The slope is 0. Right? You see that the tangent line slope changes, right? As you take different points, the tangent line has different slopes. Is everyone all right? I know this is just a little bit abstract, but I hope you're getting this. What I'm trying to show you is this notion of the slope at a point. Okay, so you take some point on your graph and you create this tangent line guy. Okay, and it has some slope. It turns out that for f of x equals x squared, the slope of the tangent line is 2x. It's always 2x. So right here, when our x was 1, we found out that the slope was 2. When x is 2, the slope here is actually going to be 4, right? At 3, the slope is going to be 6, right? At 0, the slope is 0. At negative 1, the slope is negative 2. Okay. Hold on. Okay, so this is how it happens, and again, we're not going to explain it until we get to calculus. But it turns out that for this function, that the slope, if you want the slope at some point, at some time, like you're wondering what's the slope at 1,000, right? Well, one way you can do it is to do this like average rate of change game, but actually it turns out that the slope is going to be 2,000. There's actually a rule that will tell you what the slope looks like. Okay. Hold on for a second while let me get to the punchline. Okay. So now let's think about the function e to the x. Okay. So here's the function e to the x. So f of x. here's the function f of x is e to the x. And here's the great property. Here's the great property. The great property of e, taking the space e, is that the slope of the tangent line at to the graph at x e to the x, the slope of the tangent line is e to the x again. Okay, so that is if we look at time one, and say, what's the slope there? Well, right, here's the graph e to the x. The slope is going to be e to the 1. This guy at this point has slope e. Right? At time 2, what's the slope here? The slope here is e squared. Right? The slope is e squared. Right? So, sorry. So, right, what's the value at this point? What's the height at this point? At time 1, well, the height is what? E, right? So the height is e and the slope is e. Right? Here at time 2, the height is e squared and the slope is e squared. Okay, the slope of the tangent line is e squared. Right? Okay. So this is the unusual, the unique property of this function. It's the only function, it's basically the only function that has this property. Okay, this is what makes it special. Another way of saying it geometrically is that if we look at the tangent line and go through that point, where's it going to hit? Well, if the height is e and the slope is e, where's the tangent line going to cross the axis? It'll cross one point over, right? Here, if the height is e squared, the slope is e squared, right? That means that if we move 1 over step in time, it'll drop e squared, right? So this tangent line will also cross 1 point over, right? This tangent line will also cross 1 point. This tangent line will also cross 1 point. All the tangent lines will cross at one step before in time. Okay, and this is the great property of the exponential function, and this is really the reason why the exponential function occurs in nature. It occurs in the growth of populations, and it can be used to model all sorts of bacteria growth,
You use this as
bacteria.
a
That's right.
Yeah.
So this is crucial. This is crucial. Lauren, what was your question?
It's kind of irrelevant.
Okay.
I don't know. Ask
Caroline, what was your question?
Does that, I was thinking of taking the derivative of the line then, because it's always, the tangent line, the slope is always going to be e to the x, does that mean that you can't take the derivative?
No. This is, so for those of you who know the calculus already, this is the statement that if you take the derivative of the e to the x function, you get back the e to the x function.
Okay.
This is that statement. Just expressed in terms, expressed geometrically. So this is the great thing about e to the x, that the slope of the tangent line of e to the x is e to the x, right? That the instantaneous rate of change of e to the x at time x is e to the x. Lauren, why don't you ask your question?
No, my question was actually about the derivative, but
You didn't want to bring it up.
Yeah.
Because there are people who haven't had.
Yeah.
It's okay. Okay. Okay, so yeah, next time we'll talk about its the inverse function log, and then I think soon after that we'll talk about using e to the x to model bacteria population growth, or decay of radioactive materials, etc. Things that some of you